Yeah, starting now.
Good day, everyone who is attending CCREEE's training of energy systems personnel on hydropower integration. If that's the meeting you came to, you are in the right place. We're going to begin promptly at 10 o'clock by my clock. Right now I'm reading 9:54. So thank you for coming early. Please hold on as we get things started for you. Thanks. Morning to everybody who is here to attend the training of energy systems personnel on the integration of hydropower put on by CCREEE in association with our partners at GIZ. We will begin in 4 minutes by my clock, so please stand by. Good morning once again to anyone attending the training of energy systems personnel on the integration of hydropower put on by the CCREEE. We are going to start in 2 minutes promptly at 10 o'clock by my watch. Please stand by. Good morning, everybody, and thank you for making the time to be with us this morning. My name is Gerald Lindo. I'm with the Caribbean Center for Renewable Energy and Energy Efficiency, and you are here to attend a session that focuses on the integration of hydropower systems into a large energy grid. I want to start by telling you a bit about this series. At the 82nd special meeting of the Council for Trade and Economic Development of CARICOM, CARICOM's leaders endorsed the methodology, principles, and practices of integrated resource and resilience planning as a preferred mechanism for energy sector planning in the member states. And it urged member states to develop integrated resource and resilience plans by 2023. The IRRP methodology requires an appreciation of the technical issues arising from grid expansion with renewable energy integration. And as the CCREEE works with stakeholders across the region towards delivering IRRPs for countries in the Caribbean, it will produce a series of capacity building sessions designed to address critical elements of the IRRP process, as well as renewable energy development and integration in general. These sessions are intended to build institutional capacity for resilient energy planning across the region. And today, the focus is going to be on hydropower. Today, we are gathering utilities, regulatory bodies, regional universities, professionals in the energy field to focus on the integration of hydropower. Now, it's going to be a bit more of an advanced session than we usually do. So we hope that any of the attendees here have some experience in engineering, maybe possibly a BSc in an engineering or relevant discipline, or at least experience in the energy industry. The expected outcomes for this course would be considerations for the assessment, installation, and integration of small hydropower projects. We're going to cover feasibility assessments for site installation of small hydro and the integration of hydropower into the grid. And we're going to take about 2 hours to do this. It's being done through our thematic hub in association with them, the Guyana Energy Agency. They take care of hydropower matters for CCREEE as we do our work in the region. A quick note on logistics before we introduce our presenter for today. We're using Microsoft Teams live events, and to manage what we expect to be a rather large volume of attendees, we've muted everybody's microphones, so sorry, but we do have a Q&A section that's going to be moderated by our communication specialist here. Post your questions there, and we'll make sure that we get to them in short order. Now, to our presenter. I'm going to queue up the presentation, and I'm going to ask that we move to the introductory slide there so we can properly introduce our presenter, Tobias Dirtman. Tobias Dirtman is a hydropower engineer. He's a MSc mechanical engineer, and he's a consultant in hydropower and hydropump storage. He's based in Germany, but he's been working for the Guyana Energy Agency since 2016 through the cooperation of our sponsors for this event, the German Development Agency, or the Deutsche Gesellschaft für internationale Zusammenarbeit, the GIZ. He was located in Georgetown from 2016 to 2018, but now he's back in Germany. He's responsible for capacity building in the Guyana Energy Agency and development of hydropower projects in Guyana. So now we turn over to him and his presentation. Please give him your attention. Thank you.
Yes, good morning to everybody. So we already had an introduction of myself. Before I start with the actual presentation, I would like to make a quick excursion to the overview about hydropower in the Caribbean. So I checked some numbers yesterday, and everything I found about hydropower installed capacity in the Caribbean. It's you have here the hydropower capacity installed in the Caribbean. So there are some really large scales, one in the Dominican Republic or in Puerto Rico. We come nearly up to 900 megawatts. So of course, smaller islands, we have like in St. Vincent, we have some stations with indeed 7 megawatt, Dominica 7 megawatts, but of course the larger ones are at the larger sites. Let's also switch to the CARICOM countries, Middle and South Africa. So we have here Belize, for example. Belize is nearly the biggest installed capacity is hydropower. It's more than 50 megawatts. So the generation is also the highest of hydropower before diesel and biogas. Also, we have the big Brokopondo Dam in Suriname with more than, I think, 185. I'm not sure if this is number correct. Megawatts. So this is also the biggest generator in the country of energy, electricity energy. Yes, and we have, so this both really, the hydropower is the leading energy source of electricity. And here is Guyana. We will come in the next page to it a bit more near. So installed capacity right now in Guyana it's here 0. It's from 2019. Now we have the first hydropower installed in Guyana in 2019. Then the potential is 25 megawatt. But this is more hydropower potential. So we will see on the next page the difference between small and large. But today we are doing small hydropower, of course. Yes, another introduction page. Maybe you can see the installed capacities. This is the blue one, and the potential. This is everything for small hydropower. So you see we have some countries, they already have developed everything what they have on potential, and we see, for example, St. Lucia or Grenada, we have still very high potential, not even installed any hydro facility. So there are some more potential, and this is just to develop potential. There are more potential we'll see later in some next pages. So one more page for the introduction from Guyana. This is where I stayed 3 years, so I have a lot of related hydropower pages of Guyana. So Guyana has a very special role in the region due to its number of rivers and the topographic factor you see here. In the west and the southwest, we have the very high elevation, so we have a drop here. A drop in elevation, so a drop means potential energy, so that means a lot of potential hydropower. So this map just shows you the explored potential of Guyana. So the large circle, for example, this is nearly some 100 megawatts. So there are large capacities of large scale, but also a lot of potential of small scale. So we see, just give you a number, 7,000 megawatt explored, secured hydropower potential in the whole country. This, of course, is mostly large and medium-sized hydro. And if we're going to just small hydro, we will come to the definition later. Here we have up to 10 megawatt. But let's say we have nearly more than 25 megawatt explored potential. So there are locations already identified. We could install 25 megawatt in small hydropower only. One more word to Guyana. So the first hydropower station was built after 20 years in Guyana. So 20 kilowatt, we're talking about kilowatt, not megawatt, in 2019. It was during my time. So GEA is now focusing the last years more and more on hydropower and hydropower development. We have in 150 kilowatt under construction right now in Cato. It's right here near the border to Lethem. And there are further projects in the pipeline, maybe a 2.5, 2.2 megawatt. Hopefully be tendered out this year. It's also in the region 8, near Lethem, near the border to Brazil. So this was a little introduction first to give you a small overview about the numbers. And now I will start with my real presentation. So training on energy systems, personal integration of hydropower. So this is, you see here the picture, the cover picture is already the Pico. We call it the size of the Pico hydropower station in Guyana in region number 1 from 2019. Was nearly planned and designed and built by the Guyana agency itself and supported with a German development agency, GIZ. So this is the first running system, hydropower system after 20 years. There were older systems in the 50s and the 60s and even in the 90s. They're not running anymore. And this is, I think, one of the first step, but important step for the development of hydropower in the region, especially Guyana, but I hopefully also think for the whole Caribbean. Let's come to the definition first. So we are talking about small hydropower. It's not that easy as it looks like. So the definition is varies around the world. Even in any country can do its own definition. So there are no standard definition in the world, but I will try to do it. So in many countries, in many people just separate in large and small. So it's very often that small is everything under 10 megawatt or 1 megawatt. But you can, it can be further divided, small hydro. So you can say small to 1 to 10. This is a very common thing. That's also very common. So around this ranges, it is very common. You can make the definition. So small hydro, we say what 1 to 10 megawatt. Mini, it's 100 kilowatt to 1 megawatt. Micro, let's say 5 to 100, and everything under 5 kilowatt is Pico. So if you have one of those names, you can really connect it to the size around. Yes, there are countries you have they do a definition up to 50 megawatt, but 1 to 10 megawatt for small hydro is very common. And if you want to go more into detail, you can use these names: Mini, Micro, and Pico. But yeah, beware, there's no real standardized definition around the world. So anyway, I will show you on the next page that we have to make a big difference between small in general and large in general. So I have here some extreme examples. So the largest hydropower plant in the world is Three Gorges in China. I think it's very famous. So it's 22,000 million kilowatts, comparing with the picture we have here on the right. This is a 1 and a 2 kilowatt machine system. So these are the two extremes I found. I think there are no really smaller turbines than this you can find. So it's very self-made constructed. And you see the difference. This is 22.5 million times larger than this one. So there is a difference in large and small, so you have to divide it at some point. So it's a technology difference. Yes, this power plant can easily supply the whole Caribbean and plus even more countries. It's one power plant, and I think it's even the biggest power plant, even comparing the fossil or nuclear in the world, producing and with a load factor from 70 or 80%. So it's really permanently a high power output during the whole season with extreme large volume. Of course, it's also a lot of economic impacts and critics, but yeah, this is just to show you the technology and the difference. So on the next page, it's also difference between, let's make an example. So we have PV modules, large PV farms, and one PV module. So a large PV farm, like even 100 megawatt or even going up to a gigawatt, is made of single modules. You see, it's single modules. You put them together in a row, and then you make the next row. So even very large scale PV systems are made of single modules. This is not the same as hydropower. We have seen here, this is the turbine from the small Pico 20 kilowatt we saw in Guyana. This is the turbine and the generator itself. And this is again the example from the Three Gorges turbine. This is one turbine, one of I think 3,700 megawatt, one single turbine. So a large hydropower plant is not made of a lot of small single turbines. It's made of large components. So at one point, the components becoming so large and so complex that it's not possible, that you need very specialized teams on every component. So a small hydropower plant, like here you see the GA is building it, the two GA engineers, they really are to manage to install the turbine, the generator, to install the electric equipment, and to do the commissioning. And if we're seeing here, this is just a generator from this turbine, a 700 megawatt generator, and you can imagine the size. So you see, this is different worlds. So we're speaking about, yeah, this is a different level. It's nothing really to do together. So there are people who doing like just a turbine, just a generator, or there are people doing small hydro at all. This is possible because of the size. So this is just to show you the difference between PV and hydro, for example. So that is why you always very often differ between small hydro and large hydro. And yeah, at a certain range, it's becoming so large and so big that it's just a special team for the turbine, special team for the construction, special team for everything. So yeah, I hope this becomes a bit clear. So, and now I will give you some examples of the size of the small hydro. So maybe you can remember, so small hydro was a division between 1 megawatt and up to 10 megawatt. This is very common. And I think you can, yeah. So I just an example here. So I have a lot of examples of Guyana, of a lot of projects that are really going on, because yeah, I have the sources. And this is a project, the 1.5 megawatt Kumu hydropower station project. It's really ready to tender out, and we were developing since 4 years. And this is a typical small hydro with 1.5. It's in the range. If we are here already on this page, we can maybe start with the main components. So I will do some little excursions. So hopefully you will get some overview about the basic components of hydropower. So let's start here at the beginning. You normally have here the river or a creek, doesn't matter. So you have water flow, and at the beginning, at the top, so you have a head here. From here to here, there's a head. In this example, you have a 200-meter head between the power station and the weir. So normally you dam the river at the top. So you build a weir, or it's called weir or a dam made of concrete mostly, and then you have a little reservoir, can be larger, can be smaller, and then from this weir you take a channel or a head race going to a forebay, and the forebay is the open reservoir bassin, and from this forebay you're starting with a closed penstock pipe, so the high pressure pipe. So you're starting here with the forebay and you're going down, and the pressure is rising. Penstock or pressure pipe is the name, and at the end you're arriving at the powerhouse. So there's a turbine going to the generator going to the transmission. We see here, and after this, using this water, the energy of the water, the water is put back to the river itself. So the complete water volume is putting back to the river itself. So everything you take here out, you take in here, you give back over the tail race into the river. So you don't really use water. You only use the energy inside the water. And yeah, because some people think you're using the water or you take some water out of it. No, you take everything what you take out, you give back without any pollution or you don't change the water itself. Yes, so example of the size, we're going to the next smaller stage, mini hydro. So this is up to 1 megawatt, from 100 kilowatt to 1000 kilowatt. So this is the Moko Moko hydropower station in Guyana. You see the picture, it's already existing. This is a picture from 1999. This was built 1999 by a Chinese company, near Latam in region 9. In Guyana, it was only running 2 years because there was a landslide on the penstock, destroyed nearly the complete penstock, and it's now under the rehabilitation. And it also should be tendered out this year together with the Kumu project you see before on the page before. And this is it was originally 500 kilowatt you see here, but now we are trying to, or we're sizing it up to 700 kilowatt. We're using better turbines, we're using better pipelines, and the volume is nearly the same, but with the efficiency is higher, so we're going from 500 to 700. And yeah, the powerhouse, it still remains, so the location remains. So it's also very common that you do rehabilitation with hydropower plants, because normally if you build a hydropower plant, it can really operate unlimited if you do a good maintenance. The next smaller size would be a micro. This is what you already have seen. It's a Hotza Bravo hydropower station in Region 1 Guyana, 2019. So comparing with the micro you saw, with the mini you saw before, the micro is just, you see, it's a powerhouse also, but it's just one single room. And the room, it's also depending on the flow and the head and the power, but just to give you a little feeling. So this is a micro, 20 kilowatts, pretty good overview. And this is even connected to the grid. You see here the pole, it's grid connected. It can also just feed into the island or for self-consumption, but this is also grid connected because we have a little grid there in region 1, and yeah, pretty small. But there's one smaller stage, so Pico, we can call it Pico. So let's say everything under 5 for the definition. And even on this picture, you see it's a very special type here. It's not a normal hydropower dam. It's a flow turbine. It's a single unit. Everything is installed in this single unit. It's flowing. It's really inside the river. You don't see it. You just see the very top. It's fixed on a rope and it's swimming in the river. And here is a turbine. It's like a propeller. Water going inside here, coming out here. Generator, everything is included. You're just a cable going from here to the land, and you can just yeah. So it's very attractive because you don't have to build any construction or concrete or solid stuff. You just order this one piece unit, put it in the stream, and you can generate your electricity. But of course, there's one. You need a high flow, a constant high flow in the river, and this is very rare, even in Guyana. So constant high means some meter per second, and a normal river, you can imagine in Guyana, you don't have this constantly over the year fast flowing. But they're very rare. Some very locations you can use it, but if you have the location, it's very attractive just to build it because it can be also built very quick. Yeah. So this was introduction on the size, on the definition. Now we're coming to the different types of hydropower plants. So you can divide it by different characteristics. So I choose the 3 ones. So run-of-river and reservoir storage. So if you're damming a river, you're always creating a little reservoir. But depending on the size, if it's a large reservoir, you have a reservoir storage power plant. You can really storage energy and regulate. And if you have a run-of-river, you can just take the flow what is right now in this second available. So without storage. Then it's very important to separate by the head. So there are high head. So the head you can use a potential energy. So there are hydropower plants up to 1,000 meters in a single drop in a single penstock. So this is then very high pressure up to 100 bars. Or you can even go to very low inside a river stream, for example, low head like 5 meters or even less. So the range is very, very wide. So the types of turbines you need is also very different, and the size of the power plant also is very different. And yeah, just directly connect to the head. We have the turbine types. I will show you the 3 main types: Pelton, Francis, Kaplan. Maybe you've heard of it. It's a pretty old designs. So the Francis was the first industrial design turbine, and yes, there are many other ones, but these are the main types, and this should be sufficient for the first overview today. So let's start with the run-of-river systems. Maybe you heard run-off the rivers or run-off-river or run-off-river system. So run-off-river means you don't have a storage. It means you take the water directly from the flow without any storage. So we have it here at the intake. So here's the intake. There's no real high dam or weir. We take the flow directly out of it, or a part of the flow, not everything. We take it directly to the channel and to the forebay. And then again, the same way to the penstock. The pressure is going high. Here is going to the turbine generator and to the transmission line to the consumer. So no dam, no reservoir, run of the river. Even we have a high head system here. It's not in the river, but so we take it out. We have a special way for it on a penstock and got out, but we don't have a storage. So this means run of the river systems. You just can take what is available at the moment. Another type, different type, is this is also very common. This is a run of river system inside the river itself. So the dam, see here's the powerhouse, and everything is built in one solid building, or in one solid block. So the dam is going to the powerhouse, and we have here the overflow. So this is the whole system of the hydropower plant. So there are no penstock or no forebay, no intakes. The intake is here, the outtake is here, so everything is in one building. So this you normally build if you have a large river, or you can have a river and you divide the river in the lower reservoir and the upper reservoir. So now you maybe the question's coming up, but we have a reservoir here. We create a reservoir. Yes, it is, but it's pretty small, and we can really use the storage factor. Maybe it's on the next page more clear. Yeah, so this is a drone picture from the site. So here would be the power plant. You see the river is very flat, so we don't have really a head we can use. But we can, with the dam we are creating an artificial head. In this example, it's 10 meters. So we have 10 meters we can use. But of course, we are creating the lower reservoir, so it's the river itself will pretty much be like it is now. But on the dams, on the upstream side, we have a lower reservoirs. But we can only take this water out of it that is flowing inside here. So the water level remains the same all the time. So it's maybe we have 10-meter water level. It's not really changing. Maybe a very bit, but not. It should be normally. On the next page, it's more clear. So this is the same dam. This is the cross section through the dam. So this is the upper reservoir and the level of the upper reservoir. Here's the lower reservoir, so the lower river level. And this head remains always nearly the same. So if it remains the same, so the upper level have to be the same. So if water flowing inside this reservoir or this river, we can only take the water out what is flowing exactly in this time in. So this is full of water. This is the higher level. The water going to the trash rack. Here turbine again. This is the shaft going to the generator. Generator is out of the water. And here's the outlet. So everything is, as you see again, there's a powerhouse and the dam. Everything is in one block, in one construction. And yes, this is also run of the rivers. It's in the river and it's called run of the river because we don't create a storage reservoir. Maybe to make it more clear, this location we were looking here. I go back. This location. This is the Demerara River near Georgetown, 50 kilometers up Georgetown. The original idea, the original plans, what was much different, was really a reservoir. So the dam was up to here. Here's the mountain, here's the mountain. So the original plans was the flooding of the complete area. And this is then not anymore a run of river, this is then a real storage. So maybe this page, we have the original plans here from I think from the 50s. The original plan was to build a dam like 50 meter high. So 50 meter high in a flat area, causing a flooding of some maybe like 40 kilometers long and 10 kilometers wide. So this is then a real reservoir you have. Maybe you can store energy for weeks and months, and you can change the level a little bit. So you can storage water for some days or for some weeks either. So you really have a seasonal storage or a daily storage or weekly storage depending on the size. But what we did now, we size it down to a 10-meter dam, and this is a 10-meter dam. So we call it now run of the river. So you can imagine if with a 10-meter dam, you're hiring the level at the upstream, or you're building a 50-meter dam. So this is creating you can't see really on the map, but this is creating such a big flooded area. At this time in the 50s, maybe it would be possible, but nowadays there's no chance to create such a big flooding due to the impact of the environmental impact. There's really no discussion about it. So 10-meter dam would be here a good solution to cause a small, to have small flooding and still working as a run of the river. You take the water you have. Dry season less, wet season higher flow. Yes. Yeah, this is the same dam. I just want to show you this. It's a hydraulic scheme, maybe a little excursion to learn about some hydropower names. So this is the same dam. We have the dam here, we have the powerhouse in the dam, but we just have the hydraulic schemes here. So we have two turbines here. So normally you have I don't know if you can see it. So it is a trash rack for the filter. Then you have a stop lock. You can close it completely if needed for maintenance reasons. And then you have a slide gate. So the slide gate you can open and close automatically within some minutes. So you can close it. So it's built redundant. and then the water going through the penstock. It's a small penstock, but going direct to the turbines. So we have the same turbines, 2 times 6 megawatts. And even before the turbine, there's it's called also a valve. Normally you have a spherical valve. It is a fast closing one. This is the important one. You can close and open it within maybe 20 seconds, 30 seconds. So this is the main closing, and this is the second closing. So you need at least two gates, two closing systems for the protection to really be protected. And yes, and then the turbine going to the generator. And what we also see here is it's very common in larger ones. We have a small turbine here, and this small turbine is mostly used for the internal consumption of the power plants. So it has a lower voltage. You can connect it directly to the consumers in the power plant itself. So you don't, because the big turbine is going on the high level and directly out to the transmission line, and the small turbine you can really use for the self-consumption and nearly for the black start. If you want to have a black start, you need some primary energy to go on. Yes. So there's a little excursion of hydraulic schemes. Yes, auxiliary power 100 kilowatt, maybe 50, maybe 100. You can just take out and use it for the self-consumption to, for example, you need this to open this valve. So if you have a blackout, the power plant cannot start without energy from outside. So you can use a small turbine. You can open it by hand, so you have energy at least to have for the electrical system and to open the gate, the main gate, and this gate. Okay, so next point are the hydropower turbine types. As I told you, I will just show you the 3 main types. What's the most common, the most maybe you have heard of the names. So sorry, it's in English, but it's indeed very easy to explain. So we have here's the head in meter, 10 meter, 100 meter, 1,000 meter. And here is the flow, the volume, cubic per second. Yeah, with the cubic per second and with the head, you can make the definition of the design. So the very first was the Francis turbine invented. So Francis is made for high volume, for high flow, and also made for mid and high range on the head. So it can nearly use for a lot of types of hydropower plants. If you're going higher head, like 100, 200, 300 meters, and you have not the high flow, for example, you need the Pelton turbine. So the Pelton turbine is a completely different type. It's an impulse turbine, and this is really made for high head. So we have the other high head, and on the next level we have here the Kaplan turbine. This is made especially for low head, like we had the river plants you see before, the Tiger Hill one. This is a low head, like 10 meter, and we have like this 10 meter in the river. Kaplan is very, very well designed for low head, and you also have a lot of volume. So if there's a typical large river with a small dam, so you need high volumes and low head. So Kaplan turbine is the best one. So everything's depending on the volume and on the head, and then you choose the turbine. Yeah, just to give you a small overview what is really available on the market. So this is the same, just more detailed. So you see here the Francis turbine again, but you can have different Francis turbine. You have the normal Francis turbine, you have the Francis turbine, pump turbine, you have the Francis turbine for high head, and so on. So we have the Pelton here. We talked about the high head, for the very high head, but you also have small Pelton. They also have a different design. And yes, for very small flow, it's also a little bit changed in the design. So, but it's all really, we have the main, it's all coming from the main ones. And we have here the, what we talked, the Kaplan one. It's, sorry, it's this one, the Kaplan, for the high flow. And there are different types of the Kaplan. The propeller one, you see it, we will come to it on the next page. And yeah, here's the propeller, it's horizontal, or it's straight. So yeah, but for you, I would say if you can have this in mind, Pelton, Francis, Kaplan, this is the main types and the most common types, especially for large ones. Yes, I will just show you the 3 main ones. It's the Pelton one for the high head. It's invented 1879, so pretty old technology. So high head, it's I think it's easy to understand on the pictures. You have the branch pipe or the pressure pipe. You have the very high pressure here. It's coming to the nozzle, and this is going directly on the buckets. So if you have the stream going on the buckets, and it's really spinning pretty high comparing with the other ones. With other turbines, it's a very high speed rotating runner. But everything is on the in a casing. So normally it's closed here, and you have a high speed runner here, and normally it's in this example you have a belt here, so it's going to a gearbox to reduce the speed for the generator. So this is a small example. We even have bigger ones. So these are bigger ones, a double one indeed. It's fixed on a shaft, directly connected to here's the generator. So pretty large generator directly connected, and yeah, this can even have some megawatts, 10 megawatts, 20, 30, 50 megawatts, depending on the size. No problem. So the next type would be the Francis turbine. This is the oldest one, the oldest industrial design of turbine types. More than 170 years ago, invented by Mr. Francis. So the Francis, he gives the name to the turbine. The principle is pretty easy. We have here a top view. So the pressure pipe is coming from here, going around in a spiral case, runs around. If you have the cross section, you see you have it here. You have it here, coming here, the big one, and then here the small one. So the water is flowing around the turbine. The turbine is in the middle, around the turbine, going here through the wicket gates. So the wicket gates is the green one. You can open and close them. You can regulate them here. And going from the wicket gate, it's going on the blades. The red one, the blades are connected to the turbine itself. And then you have, water is going to the blades and spinning the turbine and spinning the shaft. Here are the bearings. It's pretty heavy machines, and then going up to the generator. So this is the basic principle of the Francis turbine, one of the oldest one. And the last we have is Kaplan Turbine, invented by Victor Kaplan. This is indeed a further development of the Francis turbine with adjustable blades. Yeah, you see here on the picture, maybe you have here the blades, and maybe you can imagine that you can adjust the angle here. It's like a propeller on the plane, so you adjust them to get a better efficiency depending on the flow you have and on the pressure you have. So it's very efficiency, and as I told you before, this is made for low head, so you have a large volume but not a very high pressure. And if you can regulate it, they regulate the propellers by itself, so you have very high efficiency and very high volume. So similar principle as the Francis before, going inside here, but propeller system coming from above, and you can adjust them to regulate the flow and the efficiency. As you see, it's turning very slow, so the rotor is very large. The generator is very large here, so to get enough speed for the frequency you need. Next chapter will be the unique features of hydropower technologies. I will compare it to other renewable energies and the unique features itself on hydropower. So I choose the four I have here. So the lifetime, hydropower is one of the oldest technologies we are using to produce electrical energy. Next, I would tell a page about rotating mass for net stabilization. Maybe it's not a very popular one, but for me it's a very important one because this is about frequency control and voltage control, and in a larger grid with a lot of renewable energies, net stabilization is becoming more and more important. Similar is the next point is the power regulation. This is also regulating this means the balancing between the demand and the generation. Not as fast as the frequency control, but as fast in some minutes. So they're connected, these 2 points. And the last point would be the long-term storage. So we are talking about storage, energy storage. So if we have a reservoir, we always create a storage. So we can really storage energy, at least in a passive way. But also energy storage is becoming more and more important, especially when we're going to want to reach the aim of 100% renewable energies, storage will be the next big thing to reach this goal. So yes, lifetime. I just have this. I found this example here. I think it's very impressive enough. So this is one of the oldest hydropower run-of-the-river plants in Germany, built 1889, and the had demolished in 2011. So more than 120 years consistent operation. Indeed, a hydropower plant can have a limited lifetime if with a good maintenance work. So if you maintain the building and the component very well, the hydro station will last as long as you need it. So some big components like the turbine or other ones last more than 40 years or longer. The building itself, if you have good concrete, it can last more than 100 years without any problems. So indeed, you can change any component or you can maintain any component in hydropower plants if you need it. So this hydropower plant can last as long. You have the flow. Normally, it's never-ending flow. So yes, indeed, it's unlimited if you have a good maintenance work. So and this house was this power house was demolished not because of not working anymore, because it was relocated by 300 meters down the stream. So it could even work operate much longer. Oh, this is one of the big points of hydropower. If it built once, you have a generation for a long time. The rotating mass, yes, this is more maybe some more a topic for net simulations, net planning, networking. So rotating mass are normally you have generators normally from fossil fuel, from diesels, normally inside the grid. So you have the momentum of inertia for conventional generators. So diesel, coal, they have generators like a hydro generator. So and this, it's called something like a flywheel. You have a wheel with a high mass rotating very fast. So it's a lot of energy in it, and this is working like a buffer, like energy storage. And if you have a load coming in or out, or a generation coming in or out very fast within seconds or milliseconds, this rotating mass, if you can imagine, this is a generator from a hydro machine, very large, rotating with some hundred times per minute. You can see the energy what is inside this machine, and if you have a load coming suddenly on it, it will run still very stable and holding the frequency of the grid. And if you're coming more and more renewables in the grid, stable systems are important. Of course, you can also have a stable system like a PV system without any rotating mass. It's possible. You could do it in an electronical way, but yes, I personally prefer rotating mass in the wheel, especially if you have it doesn't matter if you have a small or a larger grid. A mass always helps to have a stabilized grid. Yes, another point would be the reactive power. We will not come to this, it would be more detailed, but yes, with a big generator, you can also control the reactive power to regulate the voltage and the voltage drop inside the grid.
Tobias, just to note, I don't know if now is an appropriate time, but we do have two questions that came in the Q&A. Right. It might be more appropriate for a little bit down the road. They want to know a bit about the process of site assessment and some of the tools used to determine feasibility of a hydropower plant, as well as the size that may be installed. So just keep that in mind as you go, please. Thanks.
Okay, how long? Yes, we will come to the point with the time. Yes, from assessment to commissioning on the next page. And yeah, the tools, I can talk about them later more in detail, but I also have the steps of developing hydropower also coming in the next chapter. And yes, I will keep this question in mind, and yeah, that's fine. So we will proceed first, yes?
Yes, please.
Okay. So next point would be power regulation. A unique selling point. Not the power regulation is very similar to the net balancing. I will try to make it on an example. Maybe it's easier. So power regulation means you have so the demand and the generation have to be in balance to have a stable system. So normally, maybe here I put a generation simulation on it. So this makes maybe more clear. So the blue line is the hydropower, the yellow is the PV, and the gray is the diesel. This is a small system of 2 megawatt, small island system near Bartica, it's called, in Guyana. So we have here 1, 2, 3, 4 days simulation. One is the rainy season, one is the dry season. So, and I will start here maybe in the rainy season. This is the hydropower. So the red line is the load of the city, going up at daytime, going down at nighttime. So, for example, in the first hours, the hydropower is exactly meeting the demand of the load. So the hydropower is adapting to the load. We have 2 megawatt available at this point, but the hydropower just giving as much as is needed at this moment. If the starting of the day PV is penetrating into the grid, the hydropower is balancing, so it's reducing its power to make space for the PV. So the whole PV generated over this day could be integrated, and the hydropower could reduce it. And this hydropower has a little reservoir, so the hydropower could storage the water for some hours and could feed it out in the night. So yes, this is, in this example, only hydro and PV is working together because the hydro is strong enough, has enough power at this time. If we go into the wet season, we have the hydropower is only 1 megawatt comparing to 1.5 or nearly 2. So the hydropower is running at full load, but even here on this little example, we have again high PV penetration, and the hydropower is decreasing to make space for the PV, that we can use the whole PV generated at this time. So we don't have surplus energy of the PV system, and this PV can storage for some hours, so it's no problem. This hydro can storage for some hours, so it's no problem that the hydro is decreasing here. And yes, so normally the diesel is doing the balancing work, the regulating work, and we see that even hydro can also do the same work as a diesel generator. Comparing with PV, because PV is not really regulatable, so the hydro is helping the PV, that the PV can integrate complete energy into the system. This is what is meant with power regulation, power balancing, also becoming more important with fluctuating generation and fluctuating demand. And another important point is now we're coming to the storage theme, long-term storage. On this picture we see this is the Suriname Brokopondo Dam, 100 megawatt or 185 megawatt. And this is really one of the largest reservoirs created, artificial reservoirs created for a hydropower plant in the 60s, 70s, early 70s, I think. You can even see it here on the maps. This is the size is really amazing. Let's see the surface, 1,500 square kilometers artificial made just for this dam. So 20 billion cubic, I think it's not really imaginable what that means. But this is a typical monthly or seasonal storage. So during the rain season, this large reservoir can really storage a lot of energy coming from the rivers during the rain season and can storage it for the dry season time. So of course you have to speak about environmental effects. This is something like this would not be built in this site. The flooding is immense, and they didn't even deforest the area, so this is causing a lot of problems. But at this time it was possible, and now it's really not an active storage, but it's a passive storage, and you really can storage the energy from the wet season. So that there's no surplus water. You don't have to leave the water unused, and you can use it later, some weeks later, some days later, some months even later. So yes, I call it passive storage, and there's even another slide with a active storage. I put it here because this is also my the work I'm working on. Pump storage systems, hydro pump storage. Maybe you know the principle. This is an example of Barbados, a simulation of Barbados. I did once in 2018. This was just a small simulation. That's just to show the size you needed and the land usage you need. So we have here a lower reservoir. We have here upper reservoir. We have a head of 260, 70 meters. I think 280 meters. So pretty high head. That's pretty high. This is what you need. So this is the top. We have a reservoir here, reservoir there, and we have the power station. It's inside the mountain. It's underground. It must be underground. I will tell you on the next page why. And when we have a virtual PV power plant, we have 1 gigawatt PV. This is just a simulation, and this is just to show you the size we would need, the land usage we would need for PV for 1 gigawatt peak, of course. And the hydropower station we have here is 200 megawatt. So we don't cover the whole gigawatt, it would be too large. We cover 200 megawatt. So, but with this gigawatt and with this storage, you can really serve the island 100% renewable nearly whole year long. Because we have it is a cross section of the system. Yeah, maybe a little bit too detailed. I just want to show you the cross section to imagine better. So here's the lower reservoir, and in the times of high photovoltaic penetration, here's a power station. So it's in the middle of the mountain. So we're pumping the water up to the higher reservoir. I think the head is here, 280 meters. That's pretty good for such a small island. So you need the head to really be feasible. So we would pump it up at daytime, and at nighttime we can use the turbines, 200 megawatt, 2 times 100 megawatt, to generate power at the night. Yes, and here are some basic designs for the simulation I was created. So the energy capacity, the storage capacity, 1,600 megawatt hours. Turbine energy or pumping is even more, nearly 2 gigawatt hours. Storage, so 2 gigawatt hours would be enough for this island with the current demand, with the current consumption. Of course, maybe the consumption will go high, but yeah, this should show that it's possible. It's possible from a technical way. Of course, it's a land usage here, but if it's built once, it will remain, and you could use it as long as you need. And yes, PV land usage is even larger, pretty large, but manageable. And this is how the simulation is working. So this is the reservoir size. At the best point, it would be full. It's the evening, and then using over the night, and in the morning it should be nearly empty. So it's a nice daily storage. So the dimension of storage have not to be a weekly or a monthly one, and it's a daily storage. So it can be, so the design is you can handle the design and the size of the design. So yeah, maybe we go here a little bit. So the yellow is the PV peak. So we're having like 700-800 going to the peak megawatt PVs of PV. And the pump storage system can only storage 200 megawatt. So we first have to use the first solar by ourselves as a consumption. Then we can storage a little bit. And in this system, everything what is going higher, we're using for the desalination. So the peak power we can use in the desalination plant, that we don't waste energy. This was just the idea not to waste any energy. And of course, the freshwater problem is also an urgent thing. So that couldn't be combined everything in once. Yeah, so that this is active storage. I think that was it for pump storage. Just to want to show that energy storage and hydropower can also mean storage energy. And yeah, hydropower pump storage is still the biggest technology around the world for storing energy until now. Yes, balancing wind and solar power. This is a good example how different sources of renewable energies can work together pretty perfectly. So I have here a wind speed recording from the GEA in Guyana near Lethem in the south. So this is 1 yearly recorded with and you see we have a wet season and dry season in this area. We have 1 wet season and one dry season. And the highest wind speed we are reaching here, so it's 8 meters per second. This is pretty good. This is the average speed, so 9 meters for average is a pretty good condition in this area. So the highest wind speed we are reaching in the very dry season, January, February, March. We have really high wind penetration, and this is enough wind to really have a feasible project at this location. If we see the precipitation rate in LATAM, so precipitation means directly the flow of the rivers and means directly the output we have from hydropower. So if it's starting to rain, we have immediately a high flow and immediately a high output of generation. So in the dry season, we have very, very low flow comparing with the wet season. So here we have the normal hydropower we can maybe just use by 20–30%. So the lowest hydropower output is exactly where we have the highest wind output. So it must not be like this, but it's very often like this, that the dry and the wet season, the wind and the rain is balancing itself. So we have a good example here how different sources of energy can work good together. So it's not a So we need them all, I would say, in this time. We need PV, we need wind, we need hydro, and this is a good example. This LATAM grid, I will come at the end to it. So we have all resources here, and they're matching pretty good together, and they're not competitive. Okay, this is the next chapter: development steps of hydropower projects in rural areas. So I will just go shortly to the basic steps you have normally in rural areas. This is very high example on the projects we did in Guyana, because in Guyana we really have spots, unexplored spots. Normally you don't have it. Normally you know the area and the topographic, but we really had some spots unexplored with no information about the topographic. So I go to the pages and what is a normal development. It must not be like this, but this is things you really normally need. And as you see here, we have years, we have months, we have days. Hydropower projects can take some time, especially larger ones can take some years easily. So this is also a new point of hydropower, because we really have constructions, we really made solid buildings, we really have to measure the flow. So let's start. What you're doing normally first, if you have a location you don't know, you do a first initial survey. So this can be a day or 2 days. You just visit the site and you take as much information as you can do with your measurements you have with you. So you can normally measure the head with the altimeter, or even with GPS. It's not very accurate GPS, but you can have an altimeter. It's a small device. You can measure the pressure even with your phone. You can measure the pressure, and then you have at least a rough number of the head. So you need the head is important, and the flow is important. The flow you can do it visual by looking at the flow first. Then you get a first impression if you have experience. If it's 10 kilowatt, if it's 1 megawatt, or it's 10 megawatt. And of course, you need electrical consumers. If you don't have any load in the region, there are good places in the region, but sometimes there are no consumers. So if there are no consumers, there's not, because you cannot change the location of the hydropower plant. So it's also you have to have in mind if there is how far they are away, and if you need a transmission line and so on. Yeah, so this is the survey of the Kumo, 2016 started, and yeah, 500 meter head. So it was also a pretty hard hiking. So if you found the station, the location is good, and the first survey, you can start doing leveling and flow measurement. So this is what you need. You need how much flow is going through it, because you have the head, that's the first, and another one is the flow. The head and the flow, if you have this, you can really enough information to design it. So the flow measurement, you do it once. It's just like a little chapter. You do the flow measurements, giving you the little per second or cubic per second, and at the same time you have to level the level of the water. So if you have the level of this water now, maybe it's 1 meter, and you have the flow. At 1 meter you have this and this flow, and you have to do it the next day and the next month and so on. And you have the leveling you have to do permanently. And at least you have to do it for at least 1 year, but better some more years. So this can be time intensive. It can take a year or 2 or 3 years. So if you don't have any data of the river, you really have to start leveling first, and this can take some years. So this can be very time intensive. If you have now this leveling logger, you're doing the data analysis. So this is a typical flow duration curve. This is the most important diagram curve you need for hydropower. So this is showing you how much power you have at what percentage of time available. Yes, we make it very easily. So we have here 50%, we have here 100%. So 50% of the time we going here on the X, we going here on this, really we're meeting 400 liter per second does it mean. So in 50% of the time we have more than 500 liter per second, and in 50% of the time we have less than 400 liter per second. So this is how you read it. And so now you can choose the design of the hydropower plant. So how much is the capacity? Of course, here we have some 10 megawatt here. Here we have just 1 megawatt. So what is the best option to choose the design? If you choose this too big, you don't have the full load hours. If you choose too small, you don't get all the energy you really can get out of it. So it's also a little bit economic calculations and even what you can. And yeah, so that's why you need this flow duration curve. This is the most important curve you would develop after having the level and after having the flow. So very important, FDC it's called, and it's the most important curve. So here are some more measurements results. So maybe you see here's the water level, 10 centimeter, 20, yeah, and depending on the water level, you have a certain flow. So you see it's not linear, it's a potential. So if we have 30 centimeters, for example, we have a flow of, in this example, a flow of 100 liter per second. But if you double the level, we nearly have 600 liter per second. So if you double the level, you nearly have 6 times, 7 times more, depending on the depending on the location. You have really much more flow if doubling the water level. And every location has a very unique a unique curve. So here you see it's the same level and flow again. So these are points you measured, the real points you measured. So like 1, 2, 3, 4 different times you measured different spots, and then you can develop a curve after it. And from this curve you can go to the flow duration curve. So the more you measure, the more spots you have, the more, and the longer you have, the better it is. But of course it's time intensive, and if it's a very rural area, you have to travel a lot and to measure a lot, and you have to be accurate, and because everything, all the design will be built on this. So all the economical design will build on this. This can show you how much power you can get out of the year. Yeah, maybe this is here a real leveling logger. You see here the hours. This is 1 year, 8,000 hours, but we are measuring every 10 minutes or 20 minutes, whether we have much more data. This is the average of 3 years leveling. So and I just translated directly to power in this example. So this is how we choose the 1.5. We have here the 1.5 megawatt. So how we choose the design of the hydropower. So we have the wet season, the dry season. We're just not coming over 1.5 megawatt, and we have the wet season. We're coming over 5 or even 10. We're going here. So we have so much power. So now you have to choose what is the optimum design for the hydropower. So we choose 1.5. So this means in this example that we have during the wet season a permanent power of 1.5 megawatt. So nearly 6 months, we have the full load, it's full on. And the rest of the year, in the dry season, you see, we nearly going to 1.5 for some months even. So you really have to have it in mind that there are times you really have very, very low output, but we also have times we have a permanently 24 hours full load 1.5 output for even 6 months. So this is also very attractive, but yeah, so it's very different to photovoltaic or wind. So it's a very seasonal general characteristic. And then at the one point you have to choose what is the best economic point. So 1.5, how much generation we can get out of it. You have the megawatt hours you can get out of it. You have then the cost, and then you will find the optimum side. Yes. So after this, you're going to your office and you do the pre-study or a feasibility study. It means yeah, depending on the size of the project, if it's a pre or not a pre. If it's a small, you do a feasibility study directly. If it's a high budget, you starting with a pre to have the first touch. So here's an example of the key figures of a pre-feasibility study. Yeah, I don't want to go now into detail, but maybe you have here very important, the annual plant output, yeah, megawatt hour per year. This is very important. So you have the load factor, so how much percentage of the time. Yes, 74%, it's pretty high. So normally hydropower is very high, can up to 80%, so 80%, 80% full load hours. So this is a very good covering. And yes, so at the end you have the capex, so you have to make an estimation of the cost. Then you have the specific cost, and then you can make the levelized cost. So here levelized cost would be 6 cents per kilowatt hour. Yeah, depending on the interest rate and the 2 years. So, but yeah, this is the pre-study. Yes, of course you need the levelized cost, and you need the characteristic, and you need the basic designs. So this could be made very clear. And yeah, so if you're sure now you want to build it, maybe you need some more information. If you have a really unknown area, like we had here in this is Kumu, it's a really unknown area. So there's no activities, no economies, nothing social or yes, economical activities. So we had to do a topographical survey, for example, of the whole area. This is the 2 kilometers line, 500 meter head. So it can be even pretty expensive to do this, but this is really needed if you want to do a tender out. You need at least this basic information for the bidders. If not, nobody will come and measure it. So you have to invest some money before at least topographic information. And the areas can be pretty large that we had here. This is a very special area, 500 meter head. So you can imagine it even takes some weeks to do at least a basic topographic area. So because you have to define how's the alignment, where's the powerhouse, and so further surveys. But we are speaking now about very special areas. This is very rural now. There are some areas you have information available already or at smaller, and then you don't need this. But this can also take time. And yes, if you have this, of course, you need the economic financing, sales price, depending on, this is like any other renewable energy or energy projects. Here you have the capex, the opex, and so on. Electricity sales, this is a very important number. So, and this electricity sales is based on your numbers you leveled, your flow and your yearly measuring of the level. So this must be accurate. So everything depends on this. And yeah, this is not, because comparing this with photovoltaic, it's pretty easy. You have a location, you can say how much you get out of here. Hydropower is very specific on the location and on the characteristic on each river. So yeah, this measurements is taking a long time and a very important role, because this can change from 9 or 10 or 20. You have to be aware of this. So yes, and this is then the environmental and the social impact. This is, I think this is the same for any project you're doing, not only energy projects. Yeah, I just copy it to show you that we have a similar requirements for hydropower. So the biggest impact for hydropower is the flooding. So flooding means the land usage. So flooding can be really a high impact. You can create reservoirs of square kilometers, as I showed you at the Brokopondo Dam. And this is normally the biggest impacts, and also a critical point. If the flooding is too large, it's hard to realize a project. And yeah, on the other side, of course, we don't have any emissions after commissioning. During the work, of course, it's solid structures. We have generated everything during the construction time, but after it's a renewable energy facility, so we don't have any emissions, and even the water itself will not be emissioned. Of course, maybe we have the conflict of if we have a river stream, maybe you need a fish ladder because you're separating the river, a running river. So maybe you have problems with the fishes, so you need a fish ladder and something like this. But at the end, it's like any other project. You need the management plan, the environmental plan, and just to show you that this abbreviations in your mind. And this, so tender construction. Construction of a normal hydropower plant at this size, if you have a good time, you need 1 year. And if you have a bad time, you need maybe 2 years. And larger hydro, of course, they can take some 4 or 5 years, depending on the size. Large hydro really can take some time, but small hydro, this is the example of the 20 kilowatt Pico hydropower plant. If you have a good team, if you have enough workers, and it's depending on the rural location, you can build it pretty quickly if you have everything there. So Yes, and tendering out. So of course, if you don't in the Caribbean region, especially on a small island or even Guyana, you need to find companies that fits for your projects. If you have a too tiny project, especially in hydropower, there's not the experience, not the capacity in the region, or maybe not yet. And so we had the problem here with a project in Guyana. We didn't find any real company who wanted to build it because there were no experience. There were no companies who did it before. So the GA built it by themselves, even the small one. So it takes some time to get the capacity and experience inside the country or even in the region. So hydropower technology is very, very special. And yes, if you don't have a, yes, so it can't have to come from abroad normally. If you have bigger projects, you need companies from abroad. The price can go up and so on. So this is one of the issues of hydropower because there are not so many hydropower plants built every year, even in the region. So there are some larger ones they built some decades ago, but they're not building a hydropower plant every year or not even every 10 years. So building up the capacity is one of the major things for hydropower in the region, especially in the Caribbean region. And yeah, at the end, don't forget testing, commissioning, handover, training, especially if everything is new. So with this, again, the 20 kilowatt in House of Row. So this is a GA engineers building their first hydropower plant alone. So there's a lot of things to do, a lot of things to learn, and of course, a lot of challenges, even if it's a small one, but it don't really differ if you have a small one or a 1 megawatt project. It's working as the same, and the problems are the same, and it's a learning effect. And testing, commissioning, and getting to the grid. So you need even personnel on site because it's a very special things you have to work on. And the maintenance and so on. So it is also a point you have to have in mind. So hydropower development can take some years, even small one, because if you're starting from scratch, from the beginning, can take some years, but it can be worse. Yes. So completing your chapter. Next chapter would be hydropower and climate change. So I didn't had a lot of information before this presentation, so I had to look out by myself. So, and this is not easy to find and give some solid results. So what I found for the region, for some forecasts for for hydropower, the most important influence is the rainfall, the precipitation rate. So this is directly the power output. So I try to find some forecast models for I have it here 2050 for the region, for the Caribbean region, and you see the red one. The red ones mean less rain than normal, and the green ones mean more than normal than today. So we have both here. So even in a small, we have here a small island. We have red and green. So depending on the elevation and so on. So it's not a clear picture what this is showing me, and there are also different models from different institutions that give more or less rainfall. So for Caribbean, I didn't find a clear, and it's even different on the countryside or on the island side, or here we see on the west side, it's getting more red. So I try to show it at one example. What does it mean if I take it? Yeah, so I have an example here. Of Guyana, I have the precipitation, the map, the general. So we have the rainforest here. We have up to 4,000 millimeter per year in the very high region, and I took just the region in the middle, somewhere near Georgetown. So yeah, the region here, region 7. So this is the precipitation is minus 100 millimeter per year change from today. So what is the normal rain in this region? 2,500 millimeter per year. So that would come up to a change of minus 4% in this region. In the next region, it would be higher again. So I cannot make a clear statement here how the effect will be of hydropower in the region. It's also because we also have big tolerances in the feasibility study itself. We have tolerance from 20 to 30% in the economic analysis, because we have fluctuations between the year of, we have some years with 50% less or more rain. So if we end in this range, like under 10%, its impact is still and I cannot really say in what direction it goes. So for me, I cannot make a solid statement of how climate change will affect this regions in related to hydropower. Another point is, yeah, we're coming to the end slowly, the integration of hydropower into the grid. So yeah, how to bring the power from the hydropower into the grid. This is normally not that easy because we have different locations for power generation and load centers very often. Because the location of the hydropower plant is fixed. There's a determination. You have the location. You cannot really choose because you have to choose. So you have to build it on the river and on the head. And yeah, so the hydropower plant is fixed. And then the next step, you have to look at the load center, where the load center is. And normally you have to build transmission lines, and you also have to take into account into the economical analysis the transmission lines. So let's have here again this example. It's the Kumu hydropower plant. This is a rehabilitation of the Mokomoko hydropower plant. You see, and here's the low center, the Latin, and it's a distance between 10 to 20 kilometers far away. So the red line, this is the transmission line. The good thing is we already have this red one existing, 18 kilometers transmission line. So you have to take it into the economical analysis if it's feasible, because these are the costs. It's only made. It's have to be only made because of the hydropower plant. And here's another one. So transmission lines are one big factor of hydropower plants to bring the energy to the load center. But in this example, they were feasible. It is 13.8 kV voltage level. Yeah, but we cannot move the hydropower, so it's at the end of the mountain, and it's here, and here's the load center. So sometimes it's happened that around the transmission line, the economical development is going higher because even small communities or houses can be connected directly to with a small substation connected along the transmission line. Yes, some more words to transmission lines. So we have examples of large-scale hydropower plants that the distance can be even several hundred kilometers if we're talking about multi-megawatt projects. And yes, we had already costs have to be included in the total cost of the hydropower plant, and the impact, the ecological impact, have also to be taken into account. If you're building a 100-kilometer transmission line through a forest, the impact is even higher than the power plant itself. So yes, look at this picture, for example, power plants through a forest. So, and you need to deforest the lines because there must be a certain distance between the line and the ground. Of course, for example, you can use this land, so you cannot be too high, but you can use it for agriculture, for example. It's no problem because the poles itself, they don't have a big land usage. Or you can even, some regions you can install PV power plants, PV modules here. It's a good area, but you cannot. You have to. Yeah, the forest itself has to be deforested because, yeah, the distance of the lines to the ground have to be a certain one. Or what is also very popular or normal, if you have an existing road, you build the poles along the road. So the land usage is you don't need a complete new alignment. You build it normally directly on the road between the field and the road. So this is the land usage is smaller here in this area. Yeah, just to show you example of this, again, Guyana. This was a big Myla hydropower project, 170 megawatts, 165 megawatt. So it's this 270 kilometer transmission line from Georgetown, the capital. The red one is the transmission line, high voltage, 230 kV, and it's going, yes, 270 kilometers. So this is a high cost. This is a high impact, and yeah, but it can be worse if there's enough generation, because here's a big drop, here's the elevation, here is a cheap cost. So hydropower location, load center can be very far, but it can be worse to build a transmission line. And of course, you need a new transmission line, even you need a new road for the access. But then very often, if you have a transmission line built along the road, along the transmission line, there can be economical development very easy, because normally there was no electricity before. So along the line, along the road, for sure, the new development will pop up, because now there's an infrastructure, and they have the road and the energy they need now. Yeah, just a master grid. Hydropower is a master grid controller. This was this example. We have the city of the community of Latam. We have here the Mokomoko Hydro again, what we saw. We have the Kumu Hydro. The Mokomoko is run-of river, no real storage. The Kumu Hydro will have a small storage. Small means 125 megawatt hours. It's not so small. And we have the PV farm plant. So the two hydros will be the controller of the grid. So this have to be taken into account. We don't have the diesel generators anymore that will control it, because the hydro will be the main generator and the highest installed capacity in the grid. And we even have the storage that have to be implemented somehow in the grid, in simulations and in the forecast models. For example, we can storage the PV and the hydro and the storage can work together, that we can at least storage the PV power indirectly. Yes, this is the same system, the same Latin system again, in a simulation, maybe to give you better overview. So we have here's the wet season. You see in the wet season, the hydro, the blue one, is really dominating. The black is just a small diesel, and the red is the PV. So if the hydro is dominating, of course, it had to be the main controller in the grid and have really to hold the grid and the voltage and the frequency as a master. In the wet season, it's a bit different. The diesel is a little bit higher, so maybe you have to switch between diesel and hydro of the controller. Yeah, so this is a yearly profile. Wet season again, dry season. Wet season we have fully water. Dry season, diesel is coming up again, and PV is a little bit up and up. So yes, here's again, this we had again during the wet season, full power 1.5 MB. In the dry season, we have to adapt to the flow. Yes, so as you see, that was it from my side. And I think we have some time for the question.
All right, thanks a lot for those, Tobias. We do have quite a few questions coming in, so I'll just go down them bit by bit. I think the very first one you've already kind of answered through a couple of minutes ago when we were talking about how long does the process take from assessments to site commissioning. Can take years, as you mentioned, but maybe you could spend a bit more time just to remind us again, what are some of the tools, physical and instruments, used to determine the feasibility of siting a hydropower plant, as well as the size of the plant that may be installed? Tobias, hello?
Sorry? No. Yeah.
Okay,
so,
you're muted.
I was muted.
Yeah,
so the software and physical instruments. So what we saw on the pages we had of the small hydropower, the most important thing we had, it was the flow measurement and the level loggers. These are the two instruments most important for measuring the flow and energy of the water. So yeah, flow measurement is, you have now instruments you can just take inside the water, you go along the stream, and it's showing you directly how much flow you have. And the level logger is just something you install at the river. You install it fixed there for some years. It's measuring the pressure, so it's measuring the level. This is the two main instruments I think we saw in some pictures. Software using of course, if you're going to larger ones or more professionals, you have very specialized software for everything. You have hydraulic. We're using normally CAD software. I mean, it's a little bit, building hydropower is also a lot of civil works. So you have normal civil calculations and civil constructions. So you have, of course, hydraulic calculations. You can do it by hand if it's small. There are a lot of companies using just Excel, a lot of Excel sheets for any individual things. So it depends. So there's a lot of instruments. and tools you can use.
Okay, very good. Question 3 was about storage. The storage dams that have been shared look significantly large. If a utility in a Caribbean island is considering hydropower, given the small size of most of the islands, how much storage would you recommend, and how much land space would likely need to be committed?
Yeah, this is so the very important of storage on hydropower is the head available. So if you have maybe if you have double the head, so maybe you have 100 meter or you have 50 meters, so double the head means double the energy you can storage. And yeah, I give this example of pump storage. So it can be feasible for larger projects because it's already existing. I'm doing some studies of smaller hydro pump storage. Storaging is a economical number, so it's the price for storage. It depends on how the system is, if the price is worth or not. So so I think there are some islands, if you have a steep mountain, a steep slope, is much better than a rough slope. So the best point would be directly on the very steep slope, maybe 50 meter or 100 meter head, and then everything depends on the price of photovoltaic, because if the renewable energy source you have, for example, you have a very cheap PV cost because they're going very down very slowly over the last years. If you have very cheap PV costs and you have surplus PV energy, then it can be the time can come to that it's feasible to storage energy. So as long as you don't have surplus energy or PV energy, there's no need. But normally, if the point is coming, maybe you have the peak of the PV during the day is higher than the consumption, then you need to storage, and then you need to have to find out the price, what it's worth to storage it. Maybe you can produce PV for 5 cents and you can storage it for 5 cents, then you still have the levelized cost of 10 cents. This can be feasible. It's very individual.
Okay.
Yes.
Site specific and also specific to a particular grid, huh?
Yes, that's so. And of course you have the batteries coming up now. They can also be cheaper. And yes, for a pump storage you need pretty much large size. And the bigger hydropower is, the larger hydropower, the lower the specific costs are. This is very important. So a large hydropower plant can produce for 3 cents per kilowatt hours, for example. A small one can easily go up to 20 or 30 and can be not economical anymore. So size matters at hydropower. So that is also a very challenging thing with small hydropower, the levelized cost.
Let me see if we can dig a bit deeper into this by looking at the example that you simulated for Barbados. And by the way, we got a question on that one. Why is it that in that example the pump storage needed to be underground? Why is that?
Maybe I can. It should be fast.
I think you passed it. Oh, so, there it is. Yeah.
Yeah. So yeah, you see the pump itself. So the pumping is the problem, not the turbine. But if you're pumping water up, you need a certain pressure before the pump. So you see the complete powerhouse is under the reservoir of the lower reservoir. So we have the lower reservoir. So this has to be at least in this example like 50 meters higher, because the pumps need a pressure before to avoid cavitation. It's a cavitation problem.
Right.
So if you have large hydro pump storage plants, they can be 50-60 meters under the lower reservoir. And the second point is that underground is very attractive because you don't have any land usage. You don't want to have a big power plant in the surface. But in this case, it must be underground due to hydraulic reasons. So it's the cavitation on the pumps is the detailed answer.
Understood. And for this specific example, and kind of going back to the previous question, how much land usage was used? I guess none for the pump and the piping in the middle, but for the 2 reservoirs, how much land usage are we talking about in this example, and how much energy was actually being stored?
I of course I have the numbers, but not here in the presentation. I mean, maybe you can. I can give you the numbers later, but maybe you can have an idea from this picture here from Google Earth.
Sure.
How much land usage. So the lower reservoir is a bit larger because it's not so deep. So the upper is a little bit higher. So the biggest land usage would be the PV field. What I marked here. This is needed for the PV, and this is the size of a 200 megawatt pump storage. There's also the idea that you can use the lower reservoir. You can use the sea as the lower reservoir. So using salt water, but salt water is very aggressive and it's causing some other problems. But there are, for example, I think there's an example in Japan. There's a 30 megawatt seawater. So the upper reservoir is just the sea itself, and you just have the lower reservoir is just the sea itself, and the upper reservoir is just you just need the upper reservoir.
If I recall, in this example, the pump storage was operational at night, and it would be nearly depleted over the course of the night. I say it was 200 megawatts. So we're talking about
200, yeah.
So it's maybe 2,400 megawatt hours, I guess. 2.4 gigawatt hours. That's just a kind of back to the envelope calculation.
The capacity was around 2,000 megawatt hours storage.
There we go.
Possible.
There we go.
I mean, this is and the design was chosen because to really to meet the daily risen demand.
Okay, that makes sense.
Yeah. So the aim of this simulation was to have a really constant 100% renewable from PV and storage during nearly. I mean, at the end, if they're going too deeper, I think 5% was still diesel because there are some days not perfectly, but like 90%, 95% you can cover with this PV and storage.
Okay. Just for context, and it's kind of connecting back to the question of, how someone decides whether something is feasible or not. This simulation, you did it in response to Barbados' aim to have 100% renewable. Is that correct?
Yes.
Okay.
So the result was the levelized cost was much lower than the diesel cost you have nowadays. This was the result.
What was the levelized cost in the end?
The levelized cost of this simulations was much lower than the cost you have today for the, I think, mainly diesel, for the fossil fuels. So the cost you have right now in the net was higher than this. This was also the aim. This was how to show it. Yeah, and one of the factors is of course that the PV costs are going very low during the last days, and especially if you have a large-scale PV power plant of 100 or 200 megawatts, you can have very good price. And because
but then again, the cost then, or the land use question, as you said, comes down to the size of the solar field.
It's a land use question. I mean, normally you can. There's a reservoir. It's a freshwater. Normally, it's a freshwater reservoir. It's similar like a lake. I mean, there are examples that you can really still use this lake as. I mean, you just have to be careful at the intake. But I know even lakes for pumped hydro storage they are using as a swimming pool, so it's okay. Water's going up and down. This is depending, but you don't have to see it as you don't have to close it completely. It can also be, and it's creating reservoir and lakes. But of course, its land usage is high. But if you can make it a little bit more attractive. But yes, the land usage is high, but comparing with batteries, if you build this pump up its run, the lifetime is much longer than batteries. So it's you have still the full power after 20 years. So it's not losing any capacity or power. So it's a long-lasting system and really should be a sustainable, reliable system.
Okay. Let me. That concludes our questions from the chat. But let me ask you one though. So go ahead.
I just see the size, 45 acre. I see the low reservoir. So this is a bigger one.
45 acres. Okay. And the upper one?
Must be smaller.
Yeah.
I mean, just an example. I mean, you can make the surface smaller and make it deeper. But this affects the turbine itself. But of course, if the land use is such a big problem or such a big price, of course you will make them smaller.
Gotcha. I want to ask a question of my own, or maybe not a question, but inviting a discussion. So the development time for this kind of thing can be years. It's obviously very, very site specific. I'm not talking about this one in particular, just hydropower in general, based on what you're saying.
Yeah, depending on
long development times.
Depending on the size and the capacity in the institution. I mean, if you're fast, you can do it in 1 year. If you have everything ready, you can do it in 1 year. So construction can be, the construction for the small was just some months, was just 3 months.
Right.
Yeah.
Well, let's talk about what you need to do to get it low. As you say, what you need to do to get things ready. I'm wondering about the role of government agencies in this sort of thing, right? Because if I'm a private sector investor and, you know, here's something with a very long lead time, here's something where I have to sort through a bunch of land use issues, I can imagine them being slow to bite on that kind of thing. And in the Guyanese case, it had to be GEA, who was kind of mission driven, I suppose. Say, you know, we're going to do this for the good of Guyana, to really show that it can be done. And, you know, they fought through all the things they had to fight through, and they made it happen. Do you think that's necessarily the case? Does hydropower need to be driven by like strong backing by the government to sort through some of these land use issues and some of these length of time issues that might scare off the private sector?
Yeah, I think the land in Guyana, the land usage was not the problem. It was more, I think it's a price comparison with the diesel generation.
Okay.
It's a price, and of course it's a mindset of want to having renewable or not. Yes, and it's very different if you talk about the large project. I mean, we have the Myla project still, and if we're talking about small hydro means a lot of capacity, about a lot of that is the reason why you need some time just to develop the capacity. If you have the capacity, then you have the engineers on site and everything, because hydropower is not very common. As I told you, you don't build a hydropower every year in the Caribbean, so you have to take the resources from somewhere else, and this can be expensive, especially small projects. It's not feasible to have designers or companies coming from abroad. So it's important to develop it locally. That is what we're trying in Guyana to make. It's not so hard to build it. You just need the practice and the experience, because it's civil constructions normally, and you're building pipes. So, and that we had troubles into getting a good price. If you don't have any bidders, or no, the tender is just, the price was suddenly double as a normal cost. So it's we need more competitors and more experience.
So having more experience in the region, you think, will help drive down those costs?
Yeah, because this little tiny project we saw in House Road, 20 kilowatt, you see what it's worth to develop it for years. 20 kilowatt, you can build a PV, but this was mainly built for capacity building, really to get the capacity to the people. So that's why I stayed there for 3 years. You have to, the beginning is very, very hard. So now we have 20 kilowatt, but right now at this moment they're building a 120 kilowatt hydropower station in the region 8. So, and we try to tender out next year 2 megawatts. So if you're doing the first steps, it takes long, but if you're in the game, and if you're having the chance to build bigger ones, like 1 megawatt or more, you can get good prices even from abroad. And it's more feasible, because small hydro can be really expensive in the specific cost. It's similar like wind power farms. Small wind power wheel is very specific, expensive. You have to come to a certain size to make it really feasible, and then it can really be then hydropower can really be a low cost.
Do you have a rule of thumb about what that size might be when it becomes commercially easier or low cost?
It depending on the head. The higher the head, the better it is. We have this project, you say Kumu, 500 meter. I mean, this is of course a dream, because you have the pressure, and you need a very small flow. Yeah, it's like a voltage, If you have a high
Yeah.
voltage, you need small current.
Small current,
So,
yeah.
so if you have a high head, you need very small flow. You have a very high pressure output, and you can build everything very small turbines, solid machines, but small and not so expensive. So if you double the head, the price can drop by like 40%.
Wow.
Of course.
All right, thanks for that, Tobias. I'm not seeing any more questions in the chat at this time, so let me turn it over to you if you have any closing remarks.
Right now I'm thinking. I just hear now upper reservoir 40, lower 45. I can see it now. No further remarks right now.
Okay, thank you very much. And not seeing any questions from the crowd. We do want to see if we can post a quick survey link to you all so we can get the audience's perspective on this particular session. We're working through some of the technical issues with that now, but last call if there are any questions before we wrap the session up. Monitoring the chat to see if there are any questions from our 25 attendees. I think we're trying to get the survey up for you all. I don't see it yet. There we go. I'm told that the survey is there now for you all. Requesting that you all who are attending just click that survey, give us some feedback on the session so we can continue to make these better for you. I'm going to wrap up the session now. I'm going to begin by thanking Tobias for sharing his experience and all this information with us, particularly interested in this pump storage simulation that you did for Barbados, because, you know, as we all in the region try to become more advanced and try to push ourselves towards greater uptake of renewable energy, we're going to need storage and we're going to need some hard thinking and creative solutions. So more work like this, I think, will be needed if we're going to try and all be as ambitious as Barbados. And I think we all throughout the region are trying to push very hard towards renewable energy. So thank you, Tobias, for sharing this and this experience. And I want to thank as well all the attendees who came out and gave their time to be with us and to absorb this information. As usual, we will be sending out the materials from this presentation to everybody who signed up. So don't worry, you'll get the information for your later perusal. And we invite you, of course, to stay tuned for future updates, future announcements, and future sessions of this nature coming from CCREEE. As usual, we are here to serve the people of the region. We are here to make sure that the renewable energy transition moves smoothly. So please give us your feedback so we can continue to do that. And once again, thank you for your time. We're going to end this session now, and we look forward to you joining us another time for another in this series of capacity building sessions for the IRRP. Thank you very much.
Thanks. Bye.